We're going to look at impulse and momentum here, and basically one way to look at this is combining concepts of kinematics and dynamics. What do we, when we're looking at things moving, and we want to talk about them both in terms of forces and in terms of kinematics, kind of what can we draw from that? So we're going to jump right into it. So with momentum, momentum is defined by the equation P equals mv, where m is the mass of an object and v is its velocity. So if an object has mass and has velocity, it has momentum. So it uses the variable p. This is a lowercase p. It has the units. Well, we can look at it and we can see what units it has. There'll be kilograms, meters per second. And it is also a vector quantity. And we know this because mass is a scalar, but v is a vector, velocity is a vector. So if I multiply a vector by a scalar, it just makes the magnitude of that vector bigger or smaller, depending on whether it's bigger or less than 1. So that's momentum. It's basically a combination of how fast, how much velocity something has, and how much mass it has. Impulse is defined by the equation I, actually doesn't really have units. So impulse is I equals net force times delta t. So again, net force delta t, it uses the variable I sometimes, or sometimes it doesn't have a variable. It has the units of, if we look at that, it's going to have units of Newton seconds. And this is also a vector, because delta t is a scalar, but net force is a vector, so this is also a vector quantity. The impulse momentum theorem is that impulse causes changes in momentum, and we can say that, in other words, net force times delta t equals delta p. Or if you prefer, sometimes you'll see it as net force delta t equals m delta v. But this first form is more generalizable. So it just says that the impulse equals changes in momentum. And so this explains why big and or fast things are hard to stop, because they have lots of momentum, and thus they require a large impulse to change that momentum in order to slow it down or stop it. So if either you've got a lot of mass or you've got a big velocity, so a lot of mass, or you're trying to have a big change in velocity, bringing a high velocity to 0, that means you need a lot of impulse to stop it. So either you need to apply a small force over a long period of time, or a large force over a short period of time. So our first example is to calculate the momentum of a 110 kilogram football player running at 8 meters per second. Compare that player's momentum with the momentum of a 0.410 kilogram football thrown at a speed of 25 meters per second. So first, we've got the momentum of the football player is going to be the mass of the football player. So let's actually call that P. So momentum of the player equals the mass of the player times the velocity of the player. We've already isolated our P, so we can say that is equal to 110 kilograms times 8 meters per second, which is 880 kilogram meters per second. And if in this case we are a little bit sloppy, this should actually say magnitude, because we need a direction. But since we're just carrying, we're assuming they're in the same direction, we can end up comparing them equally. So then similarly, we should also have magnitude here. So for our football, PF equals the mass of the football times the velocity of the football. That's going to equal 0.410 kilograms times 25 meters per second. 25 times 0.4 would be 100, would be 10. 10 plus 2.5, so this I believe should be 12.5 kilogram meters per second. If that's incorrect, leave a comment or catch up with me in class, but I think that's correct. If it's not, obviously you can use a calculator to check my quick mental math. So we notice that the momentum of the football player is much larger than the momentum of the football. And this kind of makes sense because if you imagine, would you rather try to catch a football that was thrown at you, or would you rather try to stop the football player? You probably want to catch the football, even if the football is moving really fast. 25 meters per second is pretty fast. Our second example, you push a 90 kilogram box with a force of 120 newtons for 2 seconds. If there is a constant friction force of 20 newtons, how fast is the box moving after 2 seconds? We're going to say this is missing. If this was a quiz question, this would be more clarified for you, but I'm going to say that this should be an opposite direction. If there is an opposing constant friction force of 20 newtons, how fast is the box moving after 2 seconds? So if in this case we've got forces and we've got times, so we're going to think that we want to do net force times delta t equals delta p, which is also equal to m delta v, which is also equal to m times v minus v naught, where v naught is 0. That's also missing from here. That starts from rest. Sorry, I was realizing I write these questions and have assumptions in my mind that I don't always get written down. In that case, we don't technically need this opposing constant friction force, because if it starts from rest, we know it has to oppose the direction you're moving. But if you want to leave that in there, that just helps to clarify it. So we need to find the net force. We know the delta t, and we know the mass, and that will let us find this v. So let's draw some diagrams to kind of help us along. Sometimes it helps to start by writing down some equations so you know how to lay out your diagram. So we're going to do a free body diagram. I'm going to start with force push equals 120 newtons, and then we're going to have an opposed force friction is equal to 20 newtons, and we're going to have a mass is equal to 90 kilograms, v naught equals 0 meters per second, and at some time later, delta t equals 2 seconds. We're looking for what's the final speed in meters per second. So like I said, we want to work with this equation, net force delta t equals mv, because this v naught is going to be 0. So net force is going to be force push minus force of friction times delta t over the mass is equal to v. Plugging in those numbers, we get 120 newtons minus 20 newtons times 2 seconds over 90 kilograms. And this is going to be approximately 200 divided by 90. So that's going to be 2 20, 23, 20. This is about 2.2 meters per second is going to be our final velocity. Not exactly, it's going to be slightly more than 2.2, but can't quite do that in my head. I want to take a second here to go over the units. So if you notice, we'll have newtons, seconds divided by kilograms. Well, if you remember, a newton is a kilogram meters per second squared. So that's a newton. If I multiply by seconds, one of these seconds will cancel from the denominator. And then I'm divided by kilograms. The kilograms can cancel, and we're left with just the meters per second on top. So that's the basic idea behind impulse and momentum. The last thing that I want to say is momentum is similar to, but distinct from energy, but it's very useful for analyzing collisions. So we haven't talked about energy yet in this video or in this unit, but just know that momentum and energy are different. And when we talk about energy, we'll kind of draw that difference out, but don't confuse the two. If we're talking about collisions, we're talking about things that are moving like this, we're talking about momentum.